Welcome back. So this is the last week of Introduction to Semiconductor Devices. In the last lecture, we have seen how optical emission is possible and what are the various materials for optical emission. So in this lecture, I would like to give you a quick overview of light emitting diodes. So the light emitting diodes and also lasers, they are actually a full, they are a significant subject by themselves, and you could go into a lot of depth. But today my goal would be to give you a basic overview. Okay, so I'll show you what are the key developments. They might seem a little disconnected, but I would ask you to be patient, and then if you want more information, you could always refer to the sources. In every slide I would put some references. You can always go back to the references and read up a little bit more. All right. So what is a light emitting diode? Well, a light emitting diode is very similar to a PN junction, right? So this is a band diagram of a PN junction in forward bias. We have seen it many times so far in this course. So essentially here we are applying a forward bias. So there is a difference in the quasi-Fermi levels. So this will be your EFN and this will be EFP, right? So the splitting of Fermi level happens because we are applying voltage. And because of this, the barrier is reduced and your electrons are injected into the P side, holes are injected into the N side. So the minority carriers are injected. So what happens after that, right? So in principle, what could happen is a hole can recombine with an electron here. Like in the P side, the holes are majority carriers and the electron can recombine with the hole and give out a photon, okay? And similarly in the N side, an electron can recombine with a hole and give out a photon. So the main distinction between a simple PN junction that we use in electronics and a LED is that we use direct band gap semiconductors. The reason this is important is we've already seen it a couple of times that your band gap, if you look at the EK diagram, so this is K versus E, right? So you have the peak in the valence band, and in an indirect band gap semiconductor, the peak in the valence band doesn't coincide with the dip in the conduction band. So this is an indirect band gap semiconductor, right? So this is CB minimum, this is VB maximum. They occur at different Ks. I mean, this K is a crystal momentum. We talked about it in the beginning, right? So essentially how the electron moves in a lattice. So now we have a lot of these electrons. If you take a simple PN junction with and you inject electrons and holes by forward biasing, what happens is you will have a lot of electrons here and you will have a lot of holes here, but they cannot recombine because when they emit a photon, you saw that the photon's energy it could be on the same order of magnitude here, but then the momentum of photon is very small. So it has to be accompanied by an emission of a phonon. And because of the second order nature of the process, indirect band gap semiconductors are not really efficient optical materials, because especially for optical emission, they're not good, okay? You can still use them for detection, but emission, they're not really good, okay? So instead, if you have a direct band gap semiconductor, the conduction band minimum will basically coincide with the maximum of the valence band. So now you can have your electrons easily recombining with holes and giving out a photon. So this is a very easy process, very simple process. So how do we quantify this emission of photons or not? So we talk of various, we talk of mainly two types of recombination processes. The first type of recombination process is, just give me a moment, reset. I'll go to green, okay, or maybe black, okay. So the first type of recombination process is what we call as radiative recombination. And we have seen that the recombination is basically dependent on the density of the excess minority carriers divided by the lifetime of R, I'll call it. Okay, this is one of the processes, radiative recombination. That means it's emitting a photon. The other process, it can be a whole bunch of processes. It can be, trap assisted recombination or surface recombination or, whatever. There are many, many different processes. So all of that will bunch into what we call as non-radiative recombination. And the rate again will be dependent on delta N. So tau and R. Okay. These are the two channels. And of course, the total recombination rate is going to be R. R can be, I can say total recombination is simply a sum of these two recombination rates. And I could just define it by delta N by tau. I can just give a name like that. So this is going to be the effective recombination time. Okay, the total recombination time rather. So now, in a light emitting device, for example, an LED, we would like the radiative process to be dominant. We don't like the non-radiative process. So the way we quantify that is by a term which is known as internal quantum efficiency. I'll define internal quantum efficiency by the symbol ERA, and that is essentially going to be radiative rate divided by the total rate. Okay, so this I'll call as internal quantum efficiency. This is an important characteristic. Okay, and if you want to talk in terms of lifetimes, so R is inversely proportional to tau, so you could always write this as tau, and radiative rate is inversely proportional to tau R, so I'll write it as tau R here. So if you have a very short recombination time, radiative recombination time, it will emit a lot of photons. And direct bandgap semiconductors have a very short radiative recombination time. That's why the radiative recombination rate is higher. Okay, so this is the main difference between direct and indirect bandgap semiconductors, because of which direct bandgap semiconductors are useful for 3-5 for LEDs. Okay, 3-5 materials. Oh, sorry, 3-5 useful for LEDs. If you just look at the IV characteristics, you make a diode out of silicon and 3-5. The IV characteristics will look similar. So this is just a schematic illustration of that. So here I'm showing you various materials and their band gaps here on the top here. So if you make diodes out of this, you just simply dope the material as P and N, and then you make diodes, then you see that the IV characteristics essentially look similar, the threshold-like behavior. The threshold shifts. The reason is we saw that in a PN junction, the maximum threshold that you can achieve is essentially when your Fermi levels, the N type goes to EC and the P type goes to EV. So the maximum VT that you can achieve is roughly about the band gap. It's usually slightly smaller than the band gap. Okay, so unless you dope it very, very high, right? So that's not a very ideal thing to do. So roughly the VT will be of the order of the band gap. So if we choose, let's say, gallium nitride devices, the band gap is 3.3 EV. Okay, so the voltage, the threshold voltage will be large. But then I can combine it with indium to bring down the band gap a little bit. Here, there is this gallium indium nitride, which has about 2.9. This is a schematic illustration, just to tell you qualitatively what is happening. Okay, so electrically, there's not much of difference. Okay, in fact, we use some of these 3,5 nitrides for high power applications. For example, let's say, in your power electronics and, switching, in the supply of voltage, supply of current to the home and all that, right? We have these high tension wires and stuff like that. So where you want to have high power electronics, which can withstand large voltages. Okay, our PN junctions will break down. Our regular silicon-based PN junctions will break down within, a few tens of volts. But you want them to withstand large voltages. So we have power electronic devices that can be built. That's an entirely different branch of electronics. That is also interesting. Okay, so we are not really touched about any of the power electronic devices. But yeah, this is the only difference. Okay, but they'll also have the same operating principle, so you could easily learn that. All right. So this is, this is how the PN junctions are different from light emitting diodes. All right. So internal quantum efficiency is one of the factors. The other important factor is what we call as external quantum efficiency. That is, it is well and good for a photon to be emitted, but will the photon be transferred outside the semiconductor? That's an important thing. And that is a concern, because if you just take a schematic cross section of a LED, it could be something like this. You can have a P region, you can have an N region, there is a depletion region. You forward bias it. We are just showing the bare minimum parts. Then there will be photons emitted. will the photons emitted come out? How many of the photons will come out, right? So internal quantum efficiency tells you for every electron how many photons are coming out, but out of the photons emitted, how many will actually reach outside? Because some of the photons can easily be absorbed in the semiconductor, right? So that is a concern because there can also be some reflections. The reason is if you think of the semiconductor as having, let's say, refractive index of N2, okay, and I'll say this outside air, right, is equal to is air basically equal to 1, okay. Inside this is N2, I'll say roughly 3.5. This is just a typical number. Of course, this is going to be wavelength dependent. We'll have to be exact about it, but I'll assume that at a particular wavelength, this is 3.5. So how many of the photons will come out, right? Some of the photons will simply hit the interface and come back, reflect. They'll get reflected, right? So this is basically going to be reflected. So reflected photons are going to be absorbed in the semiconductor, let's say, or they can just go multiple cycles and then they get eventually absorbed. So what is the reflection coefficient when you have this difference in refractive index? Okay, so the difference in refractive index will lead to what is known as Fresnel's reflection coefficient. So R, that is simply given by N2 minus N1 divided by N2 plus N1 whole square. Okay, so how much will that be? Well, if you take N2 of 3.5 and N1 of 1, so this is going to be 2.5 divided by this is 4.5. So this is 5 by 9. Oh, sorry, this is a square. So how much is this? 25 by 81. Okay, roughly. Now I'll just say 1/3. I'll approximate it by 33%. Okay, I mean 1/3 will be 25 by 75, slightly less than 1/3, right? So 33% of reflection. So if you emit 100 photons, 33% are actually getting reflected. Only 66% are coming out. And this is known as external quantum efficiency. I mean, there can be other things, some of them can be absorbed also. So effectively, external quantum efficiency quantifies, EQE quantifies the number of photons emitted divided by number of photons generated. Maybe I should not call it emitted because that might be confusing. Number of photons reaching outside, escaping semiconductor, right? So what is the way? I mean, this seems like a large number. 33, 1/3 of the photons are getting reflected. That's not a good thing. So in the semiconductor LEDs, if you noticed, you would see that you will have a LED chip, which is, let's say, some PN junction and all that. There is some chip here. Let's not something. On top of it, you will see a dome-like material, something like this. Okay, some curved shape. It looks like a glass. Okay, so this we call as epoxy encapsulant. Basically, you'll use an epoxy. Epoxy is type of a glass, you can think of it, and then that will surround the material, because of which this can have a refractive index of, let's say, 1.5. Okay, if you have a refractive index of 1.5, now what will be the reflection coefficient? Now R is going to be N2 is N2 is 3.5. Now N1 is 1.5. So 3.5 minus 1.5, 2 by 3.5 plus 1.5, 5 whole square. So 4 by 25, right? So now it is much smaller, 1/6, right? So this is about 16%, right? Roughly 16.5%, something like that. So we are managing to have less reflection, and this is kind of shaped in a way, shaped in a curved way so that most of the photons will finally come out, okay? And there's a lot of research ongoing about, using high index epoxies or, graded index epoxies and things like that. So to basically to enhance the collection, improve the collection efficiency of the light emitted in a LED. Okay. So I just picked up a few images from the web. So basically, these are how LEDs look like. If you break open one of the lamps in your home, you will find something like this. There'll be a chip. Sometimes you might find something small encapsulant surrounding it. The size of the chip is quite small, and I mean, you could try it as an experiment, for some projects, break open a tube light and see what kind of chips are there, and you try to apply a voltage to that with a battery, and you will see it glowing. It's fantastic. I mean, you should try it out. You can explore, or take a broken LED, LED tube light which is damaged, and you can experiment with that. You can actually open it, and you'll see a array of LED chips on it. Okay, you can. I mean, there are even YouTube videos explaining how to check them and all that. Okay, so if you're interested, you can always take a look. All right. So this is the these are the two parameters. Of course, there are a few more things. We can always get into a greater and greater amount of detail, but I think for this course, internal quantum efficiency, external quantum efficiency are the main things that I wanted to touch upon. And we also mentioned that you can tune the wavelength, right? We can't, of course, have semiconductors at every particular EG, right? You can change the composition of the semiconductor by changing the mole fraction. This is what we discussed. In the last lecture, we talked about gallium arsenide phosphide, wherein if you change the X, right, which is a mole fraction, if X was, I think we changed X equal to 0 to 1. So if X is less than 0.45, it was direct band gap. And if it was greater than 0.45, it was indirect band gap, if I remember it correctly. Okay. So now, what happens is, as you change X, you can try to look at how EG changes. On a curve, we showed you that there is a line that is showing, but how did you determine that? Well, it turns out that you do experiments and figure out those things. Okay. So this is one such experiment which shows you the LED emission as a function of, it says wavelength, but in fact, if you look closer, actually, this is based on changing mole fraction. Okay, mole fraction. So if you change the mole fraction, you're changing band gap, and because of that, the emission is changing. So you see increasing X, this is basically. Okay. So, and you see that the brightness of the LED, you fix the amount of current that you're supplying into the LED. So larger the amount of current, you get larger photons, right? Number of photons. So, and you see that at a certain wavelength, there is a peak. I think this peak turns out to be, for this particular case, X is equal to 0.4 or so. Okay. So gallium arsenic phosphorus, right? Gallium arsenic 0.6, phosphorus 0.4. These devices will give you a light emission at lambda equal to 650 nanometers. Okay. In fact, this is experimentally shown. So this is taken from this. The textbook refers to this particular book, which has a lot of information. Okay. But that's really a lot of information for you guys. I just wanted to point out this thing for you. Okay. And if you continue further increasing X, it becomes indirect band gap semiconductor, and because of it, the efficiency of light emission reduces. So you might ask me, why is this peak here? It turns out that there is a lot more physics behind it, and I don't want to get into it right now. Okay? I just want you to accept that this is the way it is. Okay, take it like an experiment. Okay, for the purposes of this course, we don't need to get into why the peaks are appearing and so on.